So chapter 7 is concerned with solutions and solution stoichiometry, and we're going to begin with giving a little bit of an introduction where we explain some of the important characteristics of solutions. So what is a solution? Well, a solution is a homogeneous mixture of two or more substances. So homogeneous means that it is the same throughout. It has the same composition the entire way through the sample. Now, when we talk about solutions, it's important to identify what we call the solvent, which is the thing that is there in the greatest amount, and there can only ever be one solvent, from the solutes, which are the things that are there in the smaller amounts, right, that are present in amounts smaller than the solvent. So if I look at something like a cup of coffee, the solvent would be water, that's the major component, and then there would be a whole bunch of solutes, which, depending on how you have your coffee, could be things like sucrose, there could be caffeine, there could be tannic acid, which gives it the nice brown color. Now, if a solution has as its solvent water, then we describe the solution as being aqueous. And if a substance is present as an aqueous solution, say we've got an aqueous solution of sodium chloride, we'll indicate that using the letters AQ following its formula. Now, aqueous solutions are important because nearly all of biochemistry takes place in aqueous solution. So often if there is water present, by default, it almost seems that there will be biochemistry occurring. So even at the very bottom of the ocean near a mid-ocean ridge, where the temperatures are several hundred degrees Celsius, the pressures are many times greater than atmospheric pressure, and there's absolutely no light, we'll still see biochemistry going on down there. In fact, when we look at other planets and we're looking for indications of life, we'll often look for water because we know that if there's water, then there's probably biochemistry occurring. And so when people, go to Mars and send probes to Mars, they're often looking for water, right? Or to the moon or wherever, they're looking for water because they know water is such a great solvent. It's very important to biochemistry. Now, these little photos here are kind of interesting. What they are rocks that have been ejected from Mars and have landed on our planet. And we can see in these photos here that there seems to be evidence of microbacteria there. So a lot of work is going on now trying to identify sources of water on Mars so that we can see if there is anything living there still. So the nature of the solvent is one important characteristic of a solution. Another important characteristic of a solution is how much solute is present. And the solutions are often characterized as being either saturated or unsaturated. And a saturated solution is one that contains the maximum amount of solute. That is, it can't dissolve anymore. So if you add any more solute to a saturated solution, it won't dissolve. Instead, it'll just fall to the bottom as undissolved solute. So often we'll use this concept to prepare saturated solutions in the lab. What we'll do is we'll take our solvent and then we'll keep adding solute to it until we have a nice layer of the solute at the bottom, and then we'll filter it off, and we know that the liquid that we have will be completely saturated in our solute. Now, an unsaturated solution is kind of just the opposite from a saturated solution. It's one that has less than the maximum amount of solute. And we can tell that we've got an unsaturated solution because if we add more solute to it, it'll dissolve and it'll just disappear into the solution. So it's pretty easy to distinguish a saturated from an unsaturated solution using this concept. Now, what's kind of interesting is that sometimes it's possible to create what we call a supersaturated solution, where we have a little more solute than what we would predict based on the solubility of the substance. So we actually have more than what would be present than in a saturated solution. Now, this is we have to do this, prepare this under special circumstances, and it's important to realize that it's an unstable situation that won't persist indefinitely. Any slight disturbance of the system, and we're going to precipitate out that excess solute once again. So it's kind of like, in the old Roadrunner cartoons when Coyote, realizes that he's off the edge of the cliff, but he doesn't kind of fall down for a moment. He gets a moment of being in that being in that unstable configuration before he plummets to his doom. So it's a little like that. It's only a temporary scenario that can't exist for very long. So a very famous substance that you can prepare a supersaturated solution of fairly easily, and you can find recipes on the internet to do this, is sodium acetate. So I'll show you what that looks like now. So here we have a supersaturated sodium acetate. So we've got a solution here. We poke it with a toothpick, a couple of toothpicks, and you can see that excess solute starts crystallizing out. Okay, now the cool thing about this is it actually gets warm. You can see here it's going up to 52 degrees Celsius when we poke it with this meat thermometer that triggers the crystallization of the excess solute. So yeah, this is referred to as hot ice for this reason. Now there are other ways of making it crystallize out. If you pour it, just the shock of moving it will cause the excess sodium acetate to move on out. So we'll see that in a moment. There it is, pouring it. So you can make these cool little like hot ice sculptures and stuff. It's kind of fun. Okay, we'll just stop that. So you kind of get the idea. So we can have a saturated solution, we can have an unsaturated solution, and we can have a supersaturated solution, which is a sort of a temporary scenario. A really important characteristic of a solution is its concentration, and the properties of a solution can vary enormously depending on the concentration of the solutes present. So a good example of this is looking at different solutions of hydrogen peroxide. So hydrogen peroxide with a concentration of 3% hydrogen peroxide is often used to clean wounds and as a mouthwash, and it's pretty harmless. Hydrogen peroxide is also used in a whole bunch of industrial processes. This is for the cleaning of baths, pools, and spas. It says it's food grade, which is kind of weird, but this is at a much greater concentration, and you certainly wouldn't want this anywhere near your skin, or definitely not in your mouth. It would cause instant bleaching of your skin, and it causes pretty nasty blisters. So the concentration of a solution, that is the amount of solute for every unit of solution, is really, really important, and you can get very different properties depending on the concentration. Now, everything we've kind of been talking about so far kind of gives the impression that a solution always has a solid component and a liquid component, and that's not actually the case, right? Solutions can form between gases, and a good example of this is the atmosphere, where nitrogen is the solvent. Nitrogen is the gas that is present in the greatest amount in the atmosphere. They can also form between gases and liquids, and a good example of this would be like, lake water. There's very obviously oxygen in a lake because, fish, right? Fish need oxygen to stay alive, so there are definitely gases dissolved in all natural waters. And then we can also even form solutions between solids, and good examples of this would be alloys. One of the earliest alloys that we made as humans was bronze, where we add tin to copper. Clearly, this is a solid. These things are both solids. And then more modern alloys would be things like steel, where we take iron and add small amounts of carbon and sometimes other metals like chromium and manganese. So it doesn't have to be a liquid with a solid. Okay, so that kind of concludes our introductory video where we explained some of the key properties of solutions.